Welcome everybody, welcome to lecture 8 uh, and in this lecture actually we will discuss quicksort algorithm and we will analyze it and we will show quicksort algorithm implementation with a Java program. So again I'm using Dr. Lee's lecture slide, so I would like to thank her for allowing me to use her slides. Okay, so let's outline. So we will review and we will analyze quicksort, and especially we will focus on the randomized quicksort. Okay, so if you remember that in our last lecture we discussed quicksort algorithm, right? So quicksort is an in place, okay, sorting algorithm. So actually although it says its names is quicksort, but it's just is a name, but it is not the quickest sorting algorithms. So in the worst case the quicksort algorithm has time complexity theta n square or big O n square for any number n, but in the best case it can be theta n log n. So in our last lecture we discussed that quicksort is implemented easily by quicksort algorithm, and so the quicksort algorithm actually it makes a partition, the array, the list, the given list is partition made is made two partitions, and quicksort itself is recursively called upon those two partitions. Okay, so quicksort algorithm is easy, but we need to understand the partition algorithm. Okay, so actually the based on the partition, okay, the efficiency of the quicksort algorithm uh, mm, uh, varies. Okay, so as we discussed in our last lecture that we may divide like this is the p for pivotal element, so we may get the pivotal elements at the beginning, or we may consider it at the end, or we may select it at the middle, or any element. Okay, so based on the selection of pivotal element, so you will see that the complexity or time complexity varies. Okay, and okay, so I like you to go through this demo, and then you will understand that. Okay, and from like your previous homework assignment, you will get I will give you some assignment and quiz questions from this chapter. Okay, most of them will be from the book. Okay, so we find that in the so okay, so in the best case in log n, right? In the best case in log n, for instance, this log n is the height, and this size n. You see that c and c and c, and so how many splits are, so total is in log n. And actually what we want to do, okay, so today we will focus on a randomized version of the quicksort algorithm. Okay, so let us go to the slide. So the slide says that actually let us do a quick review. So the quicksort algorithm, its main part is a partition method, right? The partition method, what it does, it makes it splits the array into two partitions, like two sides, and right, and on the left side we see that the all elements in the left side become less than the pivotal element, and all elements on the right side are the greater than from the pivotal element, in case we are sorting in ascending order. okay, but if you want to sort in descending order, then it will be in reverse order. Okay, all the elements on the left side will be greater than the pivotal element, and all the elements on the right side will be less than the pivotal element. So here is the so the efficiency of the quicksort algorithm depends on the partition. So if it is a good partition, then efficiency is short, and if it is bad partition, then efficiency will be worst. And in the worst case, we saw that the efficiency is theta n squared. Okay. Okay. So, but in the best case, we see that the efficiency will be n log n. Okay, actually it will be n, not m. Okay. Okay, and so okay, so now we see that in the quicksort algorithm there is a recursive method, right? So the recursive method happens on the both partitions, both on left and right partitions. So for instance, if we have an imbalanced partition, then we will have, for instance, one side is no element or one element, and the other side is n minus one element, and then again partition is one side another element, another side is the remaining elements. So in that case, you will see that this is an imbalanced partition. So in that case, the complexity will fall into worst case, and in this case the complexity will be theta n square. Okay, but on the other hand, if we have a good partition or balanced partition, then or pretty balanced partition, then we will get the time complexity in log n. Okay, so like same as merge sort algorithm. Okay, so we can see, for instance, if we have a pretty balanced balanced partition. For instance, give me 1 second. Okay, so here, for instance, this is for an unbalanced case. Okay, so for instance, one side 1/10 of the elements, and another side is 9/10 of the elements. So that will be an unbalanced situation or partition. In that case, we know that. So the efficiency will be theta n squared. But if we have a good partition, then we will see that we will have complexity is n log n. Okay, so now, so I like you to read the book. So the book has a good description. Okay, so that like the analysis of quicksort algorithm, here the informations are here, so please go through and then you'll understand this. Okay, you don't need to go in depth, so we don't need to go in depth analysis for this, but we need to so let's see, we need to understand just another thing, that what is that? This one, randomized version of quicksort. Okay, so actually what it happens, actually say the partition, if we make a partition around a random element. Okay, so the good partition would be if we can partition at the middle. Okay, for instance, one, so for instance, if we have some elements, okay, so some elements, there will be middle elements. So one side, so for instance here, this side there will be some element, another is pivotal element, okay, and another this side there will be the remaining elements. Okay, so if it is in a balanced position, then we will get a good time complexity. However, if the partition is not balanced, so then we will not get good time complexity. So the randomized version, it says, so the partition around a random element. So what is the random element? Okay, so it can be the first element, or it can be the middle element, or it can be the last element. Okay, so then in that case the running time is dependent to the input order, and no assumption need to be made about the input distribution. So no specific input actually input behavior. So now let us go through actually some ideas. So the idea around behind the randomized quicksort is that, so for instance, instead of always using AR or AP, P is the pivotal element, as the pivot, okay, so select a randomly chosen element from any element from array, so P to R, these are index. Okay, then we do so by first exchanging the element AR with an element chosen a random position from between P to R. Okay, P is the pivotal position and R is the last position. So in that case, what could happen, for instance, any element, for instance say earth element, or if we say X, say pivotal element equal to X equal to AR, so is equally likely to be any element that is so if we have one element, right, so here as pivotal element, so how many element will be, the remaining element will be R minus P plus 1, okay, in the subarray. Okay, for instance, let us see here. Okay, so here if we get focus here, we will see that, okay, so if we make 0 and n minus 1 split, okay, so that means total how many elements, total there are n elements, and in one side is no element and another element is the pivotal element, and the remaining element will be n minus 1. The total is 0 plus 1 is a pivot element, and n minus 1, then is totally is total n, right, 0 plus 1 plus n minus 1, the totally n elements. Or another thing, it can be happen, one side we can have one element and the pivotal element will be the after one element, the second element pivot element, and then the remaining part will n minus 2 elements. Okay, so the total will be 1 plus 1 plus n minus 2. The total will be every case is n element. Okay, the split is will be one side is 1 and another side will be n minus 2, and similarly it may happen that on one side n minus 1 element and then the pivot element, and another side is 0 element. Okay, so that is since over here, still over here n minus 1 plus 1 plus 0, that is will be n element. Okay, so total will be, so total time complexity, if we do this, then it will be sum of these plus this, right, and what will happen over here, we know that this part, okay, will so like an equation, some mathematical equation, then it will be n squared or k squared, we can say n squared. Okay, so then total will be, if you take the calculation, the total will be n squared. Total will be n squared. Okay, so that time complexity will be n squared. Okay, the thing is that we can see 1 plus, what is that, maybe something like 1 plus 2 plus 3 plus dot up to what is called, say, n minus 1, right? So then it is sum equal to so like this one, right? So 1 plus 2 plus 3 plus dot up to n minus 1. So this will be n into n minus 1 divided by 2, right? Sum is this one, right? So that means it's total n squared, right? So then it will come up with time complexity will come up with theta n squared. Okay. So something is here. Okay, so it will come up with a theta n squared. So time complexity will be theta n squared. Okay, so that's all. Please read the book, and read the book, then you will see that so it is like some small quick discussion. Okay, so now I would like to go to a live program to discuss the Quicksort algorithm in one of the programming languages, okay, like C++ or C# or Java. Okay, so if you go to my account, replit.it/@ my username Mokhtar, KTER. So I think oh, I need to log in. Let me log in to my account. Okay, so Quicksort Q. Okay, so here I have a program written in Java. Okay, so here Quicksort. Actually, okay. So this is another version of Quicksort algorithm. So okay, so here my Quicksort class, and then this is the Quicksort method, and it takes an integer type array, and it has lower index and low index and high index. Okay, so if array is null or empty, then it will return. Okay, otherwise if low is greater or equal to high, then if low value index is greater or equal to high, then it will return. Otherwise, okay, so here we are getting midpoint, and then I'm considering that my pivot element, initial pivot element, is the midpoint at a mid index. Okay, so here here. So while this is hold on a second please. In our previous so here the partition is kind of partition method. Okay, so here so although it is named Quicksort, you can make it partition method or whatever you would like, but actually the partition is inside over here. Okay, so here until this part is partition. Okay, so while I less or equal to j, that means this part is okay, then and while array index I is less than pivot, that means all if the element is less than the pivot element, then what do we want to do? We just increase the I. Okay, and similarly if the value right side, so this is the left side. Okay, the left side of pivot element and the right side of the pivot elements. Okay, this is the pivot element, right side are greater than, so then the pivot the element, then we decrease j. Actually what happens over here, so let me draw it. So here is the pivot value. Okay, and then we are starting I over here and j over here. Okay, so what we are doing, if this value is less than the pivot value, then we are going to the next element. Okay, I is increasing, I is moving to here, and then we are checking if this value is less than the pivot element, then we are moving to the next element, okay, from the I and moving right. Okay, on the other hand, what we are doing, if these, that means these are in position. Okay, we don't for the first phase it is fine. Okay, otherwise if we see that this value, for instance this value will come from right side, this value is greater than the pivot element, then we don't need to, then what we will say, we will come to the next, the left side, j we will come next, so then j will be here. After that, if we again we see this value also is greater than pivot element, then we don't need to do anything, we just will move over here. Otherwise if we see any value is, like for instance this value, any value is less than the pivot element, okay, then for any value here from left side is greater than the pivot value, then we need to swap this, right? We need to exchange this value with this value, these two values with these values. So here is the swapping. Okay, here is the swapping. Okay, and how long will be swapping? As long as I, so I will be increasing from this left to right and j will be decreasing from right to left. So as long as how long we will continue this? As long as I and j become in one position, they do not pass. I cannot go to j, right? Exit j, I cannot exit j. Okay, so here this is the condition. Okay, and same condition is over here. Okay, as long as this condition is true, then we will continue this. Okay, and here this is the, so until this, so this is the Quicksort. Okay, and so this is swap method, and this is my main class, and then it has just print array, and it has main method. So in the main method I have an array. So I have an array of integer type array with this element. Okay, how many elements I do? 1 2 3 4 5 6 7 8. Okay, so let us make one more 40. Okay, 9. So I will say, so here it will be initially it will be printing unsorted array, and then later we will call the quicksort, and then here we will call the quicksort, and then we will pass the array, and this is the pivot element, and this is the left low index, okay, sorry, this is the low index, and this is the high index. So high index will be length -1. Okay, that's it. So if we run this program, it should work. Okay, so here unsorted array is this, like, and then sorted array will be this. Okay, now I like you to think about this this implementation, or you may make a slightly different, a little bit different implementation over here. Okay, but one thing that I like you to do some practice. How do you sort this algorithm in descending order? Okay, for instance, this sorting is in ascending order, right, from smaller to the greater element to the greatest element, from the smallest element to the greatest element. But if you understand this code, and then you will see easily within only just 2 changes you will need to make this sorting in descending order. Okay, so you see that I have made some changes in my program code, just only 2 changes, and then if I run this program, it will display the array in descending order, right? So now it is your task to analyze this algorithm and to figure out what are the 2 changes, that just 2 changes that I have made in order to make this algorithm in to display in descending order. Okay, now I can quickly come back to the algorithm and to show you that if I, as long as if I undo the changes, then it will display in ascending order again. Okay, so so this is the this is the my program URL, and it is in Java. I think you can do it quickly using C#, okay, and C++. So there are only minor changes. Okay, just output statement change. You will change the output statement. Okay, and I found a good intuitive visualization of the quicksort algorithm on the internet, so then you can practice it. Or if you do a Google search on YouTube, do a search on YouTube, you may find a like many many intuitive visualization of quicksort algorithm. Okay, so this has a kind of visualization, or I like you to do the Google search, then we'll see some. Okay, and that's it for now. And then please follow the course schedule, and please complete the assignment 2 and quiz 2 by this weekend. And I will have another quiz from this chapter, uh, from the quicksort algorithm, and I may have another assignment, and I will post it in detail by this weekend. That will be due by the next weekend. Okay, and so thank you so much. So please read the book and the slides and have some practice. Okay, thank you so much. Bye bye.